Hello everyone, I'm Feiyu Chen from Guangdong University of Technology. Today, I'm going to present our work, EAULV8, an enhanced crack segmentation algorithm for infrastructure maintenance. Let's get started. First, let's go to the introduction part. Infrastructure safety is very critical, but cracks, key indicators of structural health, are hard to detect accurately. Traditional manual inspections are labor-intensive and subjective, while existing deep learning models like YOLO still struggle with two issues: poor use of spatial information and imprecise boundary detection. As shown here, cracks vary in different shapes, lightnings, and backgrounds, making them challenging. Our goal is to develop a better algorithm to tackle all these problems. Now let's look at the objectives. Current techniques face three main limitations. First, cracks have complex morphologies. Think irregular widths and branches. You can look at the first pictures. Second, background textures often get confused with cracks, and you can look at the second pictures to comprehend it. Thirdly, boundary precision is also very low, especially in low contrast areas, which is shown in the third pictures. So we aim to enhance two things: crack localization precision and boundary segmentation quality, making automated maintenance more reliable. Now let's look at our method. To solve all these problems, we introduced two innovations. First, the efficient local attention, or ELA. It uses strip pooling to capture vertical features, and we use 1D convolution to connect long cracks. We also use group normalization to reduce lightning interference. We also integrated this into ULV8's C2F model to boost spatial features with little extra computation. Second, our adaptive region-specific loss, ARS loss, which is also a very new loss functions in crack detection. It divides images into 256 subregions, calculates false positives and negatives, and adjusts penalties dynamically. This helps the model focus on tricky boundaries, working with standard losses to refine edges. Now let's look at our results. On the Roboflow dataset, EAULV8 achieves 85.67% precision, 10% higher than ULV5 and ULV11, which is the newest model which Alteryx invented, and 5% higher than original ULV8. It also outperforms others in MAP 50 and F1 score. Visually, you can see fewer false positives and smoother edges compared to baselines. For example, EA-UV8 avoids mistaking textures for cracks, which is crucial for reliability. In short, ELA improves spatial localization. ARS fixes boundary issues, and together, EA-UV8 outperforms existing ULO models. This proves is practical for real-world crack detection. For our future work, firstly, we want to enhance the feature pyramid to boost recall, especially for tiny cracks. Secondly, we also want to integrate CAM for weekly supervised learning to reduce annotation efforts. Thirdly, we want to add a length prediction branch using methods like orthogonal skeleton lines to provide quantitative metrics for maintenance. Our work builds on these key references, including ELA and ARS loss functions, and ULO frameworks. You can feel free to check them later. That's all. Thank you very much for listening my presentation. I am very happy to take your questions, so you can reach me via my email, LinkedIn, and my WeChat.